Temperature: 7,500 to 10,000 Kelvin. Mass: 1.7 to 2.2 times that of the Sun. Luminosity: 38 times that of the Sun. Lifespan: only 400 million years. These numbers do not describe some sci-fi weapon, but rather one of the most ferocious celestial beasts in the Milky Way, the A-type star. In the upcoming video, we will explore the astonishing characteristics of these blue-white giants together. A-type stars occupy a special place within the stellar family. They are hotter and brighter than the Sun we are familiar with, yet not as extreme as the outrageous O-type and B-type stars. If we were to compare stars to cars, our Sun would be like a reliable family sedan running steadily for 10 billion years. On the other hand, A-type stars are the supercars of the cosmos, stunning, fast, attention-grabbing, but destined for a short-lived existence. Imagine standing just 1 million kilometers away from the surface of an A-type star. What would you see? An intense, blinding blue-white light, so luminous that it could roast marshmallows on Pluto. This color reveals their extremely high surface temperatures, far exceeding what we might imagine. Let's take a look at one of the most famous A-type stars, Vega. Located just 25 light-years away from us, Vega is the fifth brightest star in the night sky and one of the easiest to recognize during summer in the northern hemisphere. Vega has a truly remarkable feature. It rotates extremely fast, completing a full rotation every 12.5 hours. This rapid spin causes Vega to become a cosmic hamburger. Its equatorial region bulges outward, shaping the star into an oblate spheroid. But that's not all. This incredible rotation leads to another astonishing phenomenon. Vega ejects approximately 1 million tons of material into space every second. Since the time of the ancient Egyptians building the pyramids up until today, Vega has shed material equivalent to the mass of 5 Earths. It's like a colossal cosmic firework, constantly spewing out scorching hot gas into the surrounding space. How hot is the surface of an A-type star really? For Vega, its surface temperature reaches a staggering 9,700 Kelvin. This number might seem abstract, so let's use some comparisons to put it into perspective. The maximum temperature of a steel furnace is around 1,800 Kelvin, yet Vega's surface temperature is more than 5 times that. At such temperatures, titanium would evaporate like water, and silicon would turn into vapor. If you tried to approach Vega, you would be completely obliterated by intense ultraviolet radiation, even several astronomical units away. The light emitted by these stars is heavily concentrated in the ultraviolet range, making them utterly lethal to life as we know it. Even with the protection of an atmosphere, any attempt at life formation near an A-type star would be incinerated under the relentless bombardment of UV radiation. Let's take a closer look at another famous A-type star, Sirius A. This star has a mass 2.05 times that of the Sun. While this might not sound like a huge difference, the impact of this increased mass is profound. If you could stand on the surface of Sirius A, not that you'd last a second before being vaporized, you'd find your weight to be 4 times what it is on Earth. This intense gravity compresses the core of the star, driving nuclear fusion reactions to occur even more ferociously. Greater mass leads to higher core pressure and a faster rate of hydrogen burning. It's comparable to a fuel-guzzling supercar, powerful and thrilling, but burning through its fuel at an astonishing rate. This is precisely why A-type stars have such short lifespans. When it comes to lifespan, this is one of the most astonishing aspects of A-type stars. Our Sun is expected to shine steadily for about 10 billion years, while an A-type star's lifespan is only around 400 million years. What does 400 million years represent? It's roughly equivalent to the time from the age of the dinosaurs to the present day on Earth. In other words, while an A-type star is still in its main sequence phase, burning hydrogen steadily, complex life on Earth hasn't even emerged yet. Once the core hydrogen of an A-type star depletes, it quickly expands into a red giant. Eventually, it sheds its outer layers and forms a white dwarf. The entire process is akin to a dazzling yet fleeting fireworks display, with a birth-to-death timeline shorter than the evolution of life on Earth. Interestingly, despite their intense nature, A-type stars rarely exhibit the kind of explosive activity seen in other stars. The Sun frequently produces solar flares, releasing vast amounts of X-rays and high-energy particles, but A-type stars remain relatively quiet in this regard. This is because A-type stars lack the deep convective zones found in stars like our Sun. The Sun's outer layers churn like bubbling oatmeal, generating complex magnetic fields whose breaking and reconnection led to flares. In contrast, the structure of A-type stars is more stable, so while they might bake you with ultraviolet radiation, they won't blast you with X-ray flares. Because A-type stars are so bright, astronomers often use them as cosmic lighthouses. For example, Vega once served as the standard for defining stellar brightness. Even today, many space telescopes use Vega to calibrate their observation instruments. By studying the spectra of A-type stars, scientists can also learn about the distribution of interstellar dust. When starlight passes through interstellar dust, it undergoes subtle changes. Comparing the expected spectrum of the star with the observed spectrum allows astronomers to weigh the dust within the Milky Way. So, can life exist around A-type stars? In theory, if a planet is far enough away to avoid the harshest ultraviolet radiation, liquid water might be possible. However, strong stellar winds from A-type stars would act like cosmic sandstorms, continuously stripping away the planet's atmosphere. More critically, the biggest issue is time. With a lifespan of only 400 million years, even if life were to begin on a planet orbiting an A-type star, it would have an extremely limited window to evolve. For complex life forms, such a time frame is far too short. It's similar to assigning a homework task. Most forms of life wouldn't even make it past the introduction before the star begins its decline towards death. A-type stars truly are the sports cars of the universe, sleek and dazzling with immense power, but destined for a brief life. They burn through their nuclear fuel at an astonishing rate, unleashing incredible amounts of energy in a relatively short span of time. In a sense, A-type stars embody an extreme cosmic aesthetic. Transient yet spectacular, fierce yet awe-inspiring. When you gaze at Vega on a summer night, remember that you're looking at one of the wildest beasts in the galaxy, a cosmic giant that is both breathtakingly beautiful and intensely perilous.